So in Unit 10, we are going to go over the modern atomic theory, which focuses on the electron. Um, Up to this point, we have been mentioning electrons sort of briefly on covalent bonding and ionic bonding and the transfer of electron, but we haven't really put so much emphasis on the electron itself and where the electron exists and what is the property of electrons. The speed of electron, for example, or the mass of electron. We didn't really address any of these topics. In Unit 10, we are going to study the electron and have it our focal point. So once we finish this unit, you will kind of have a more sophisticated understanding of the description of electron. So up to this point, every time we talk about the electron, we kind of draw an analogy between the solar system and the nucleus and the electron. So we kind of refer to the nucleus similar to the sun, and where you have the electron basically orbit the sun, similar to the nucleus, similar to all the planets that orbit the sun. Later on, once we finish this unit, you will find out that this is actually an oversimplification to try to understand electron back when we were studying chemical bonding, because again, our focus was not really the electron itself, rather we were focusing on the chemical interaction. Okay. Most of the modern description and most of the modern studies for electron is based on nuclear physics and complex math. Today, the good news that we're not going to focus on any complex math, nor going too deep into any nuclear physics. But our goal here is to expand our boundaries and try to understand the electron in depth, a little bit more than what we have been talking about for the past several weeks. Okay. We will find out, for example, that it is impossible to know exactly where the electron is, okay, or where the electron is doing. And that's for a few reasons that I will go over in a second. So, when we are dealing with a complex problem or a challenging problem, what we try to do, we try to either draw an analogy, so something that we are familiar with, so we can understand the problem and try to find a solution for the problem in a more relevant way to us. And we also look at probabilities. So, in order to accommodate the uncertainty of electron or where the electron exists, the electron position and motion, we refer to where the electron probably is within the atom and instead of where the electron exists exactly or definitely, because we are not going to be able, and even up to today's, no one is able to say this is the xy position of where the electron is, because it is not possible. So you will see me throughout the lecture, I will always refer to the position of electron with high probability. So this is probably where the electron exists, and we're not going to say this is where the electron exists because we can't really tell. Okay. So when it comes to analogies back here, we are going to take, for example, the guitar string to help us study the wave properties of electron, because we're going to address electron as two different object with two different properties, as a particle and as a wave, as you will see later. So in order to communicate something of that nature, of a wave property, scientists often use analogies. Okay. So when we are going to study the wave property of electron, as I mentioned earlier, we are going to start with studying the guitar string. Okay. Because it does help us study the wave property of electron. So this is a kind of an introduction for the objective of this unit. When it comes to history, obviously Einstein is one of the pioneers when it comes to studying electron. Okay. Um, he showed and he demonstrated that the electromagnetic radiation, or the EMR, has the properties of a matter as well as a wave, and he was the first one to introduce the concept of wave particle duality of light. So the light has the properties of wave and has the properties of a particle in the same time, and we will see exactly in a second what does it mean to have a wave property and what does it mean to have a particle property in the same time. Another scientist that was going hand in hand with Einstein when it comes to addressing the electron and the electromagnetic radiation is the French scientist Louis de Broglie. He wondered that since light normally thought to be a wave, is it possible that the light also has a particle property? Could matter, specifically the electron, normally thought to be a particle, have also wave properties? So Einstein and Louis de Broglie is one of the first two scientists that investigated electron and studied electron, even with the limited resources they had back then. Most of their findings and most of their achievement, it was done through calculations and mathematical calculations. Again, because back then, the techniques that are available now was not there for their days. Um, when it comes to the electron travels in a really high speed, magnificently high speed, 1 times 10 to the power 5 meters per second. It has a wavelength of 7.3 times 10 to the power negative 9 meter. This wavelength is about the same size as the radius of the atom. With this high speed, the electron can orbit the hydrogen nucleus over 3 million times in 1 second. So you can imagine how fast the electron is going. And this is one of the reasons that we can't really tell where the electron position is precisely. The reason is by the time you say this is where the electron is sitting right at this moment, guess what? The electron has already changed position and has traveled somewhere else. Treating the electron as a wave just might be the right way to handle this problem. So, due to the inheritance difficulty of studying the position of electron, we're going to focus at this point at the wave property of electrons. So we can study the intensity, for example, of the negative charge through the study of the wavelength. So scientists are fascinated about the electron, and many scientists try to measure the speed and also the position of electron. A scientist called Heisenberg, he came up with a concept or a new principle called the Heisenberg uncertainty principle, which states that it is impossible to experimentally determine both the position and the speed of electron at the same time. The reason for that, because the electron is very small and tiny, moving at extremely high speed. So the simple act of trying to measure the speed or position would change either quantity. So if you're trying to measure the position of an electron, by the time you measure the position, the electron has traveled so much and so much speed and so much distance that the speed cannot be determined accurately at that moment. And if you're trying to determine the speed of electron, the position cannot be determined at that moment. So you can determine either one, but they have to be separately measured or experimentally determined. This is one of the famous quotes of Einstein, where in summary he states that we have no choice but to use the two concepts of wave properties and particle properties in order to study and understand the properties of light and electrons. Okay. Um, when we are talking about the dual nature of electron as a particle and as a wave, so in terms of particle properties, the electrons are very small and tiny. It has a negative charge. Obviously, at this point, we all know the electron is negatively charged particles, and it has a mass of 9.1096 times 10 to the power negative 28 grams. So it's very small and tiny. You can tell from the mass of that particle, yet it travels in a very high speed. Okay, when it comes to the wave characteristic of electron has an effect on the space around it. Okay, can be described as a wave of varying negative charge intensity. So as the electron travels around the nucleus, the change in intensity of the electron of the negative charge, that basically represents a wavelength. Okay, so as the wavelength increases, the intensity of the negative charge increases. Okay, as the wave as the intensity of the electron charge decreases, the wave the intensity of the wave also decreases. So again, when we're talking about the wave characteristics, we're not mentioning the particle. We don't really care about how big the electron is or how fast the electron is going. We are focusing solely on the wave characteristic of electron. And same thing when we talk about particles. So, what we are going to do now, we're going to study the wave properties of electron. So we're not going to focus on the particle characteristic of electron. And when we study the wave of electron, we're going to use the guitar string as our model um, to study the wave properties of electron. Now, every time you play the guitar string, the movement of the string up and down, it is considered a waveform. Okay, we call that as a waveform because every single movement has a different unique shape, correct? So these shapes of the string will generate different waveforms, will generate different sounds. Um, we call these as waveforms. Same example applies to the electron. Every time the electron moves around the nucleus, the intensity of the negative charge varies from one area to the other, which would generate a different waveform, a different wave shape for that movement. So we call that as a waveform for the electron. The intensity of these waveforms, it depends on the intensity of the negative charge. So whenever there is a high volume of negative charge, you would see there is a really vigorous movement of the waveform. When there is no intensity of negative charge, there is no movement of the electron, you would see there is no waveform, or the waveform stop moving. And in this case, we call that as nodes. So the nodes on the waveform are the areas where the electron is moving, where the negative charge is not detected at all. So that's what we define the nodes. So going back to the waveform, now even though it might seem that we have a really large number of waveforms that are possible from the playing of the guitar or the plucking of the guitar, um, the the number of these waveforms is limited. So it doesn't really go to infinite number. It is a finite numbers of waveform. And so is the case for electrons. So even though the electron um, is moving in the space around the nucleus, generating all these waveforms, even though that number of waveform that's coming from that movement seems to be a really large number of waveforms, but at the end of the day, it is a finite number of waveform, and this is how the electron is usually defined. Okay, so a few things I would like you to pay attention to. Number one is the waveform. What does a waveform mean? So the waveform means it's the wave shape that is generated from the movement of electron. Okay, similar to the string um, played on the guitar. And again, when we say the waveform, we don't really care if the guitar string is made from plastic or it's made from any kind of different material. We're really not focusing on the string itself. Rather, we're focusing on the sound that it's coming from the string on the guitar. We're focusing on the waveform. Okay, so waveform, that's the first thing I would like you to focus on and understand what is a waveform for electron means. Number two, the nodes. Why do we have nodes on waveform? And nodes is when the electron is not moving or the intensity of the negative charge is very low. Um, Better defined as there is no movement for the electron. Now, the last thing that I would like you to be familiar with is the concept of stationary waveform. So, if you were to take all these seven possibilities, configuration possibilities for these waveforms, and you superimpose them on top of each other, it will seem as a string is not moving. So, the string itself, it might seem that it's not moving, but the waveform is still generated, and that's what we call a stationary or a standing wave. A standing wave also mean a stationary wave form. So a standing wave, even though the string is not moving, but the waveform is still generated, and that's what we call a stationary waveform. So it means as it is a stable waveform that is not moving, but the waveform is still generated. So, what does a wave character of an electron mean? Just as, again, we're going to summarize everything one more time. Just as the intensity of the movement of the guitar string can vary, so can the intensity of the negative charge of the electron can vary at different positions outside the nucleus. So when the electron moves around the nucleus, the intensity of that movement can vary from one area to the other, which would generate different waveforms because of that movement. The variation in the intensity of the electron charge can be described in terms of a three-dimensional standing wave, like the standing wave of the guitar string. Okay, so that's what we talked about, the stationary wave. When you superimpose or overlay all these waveforms on top of each other, it seems like as the string is not moving, but the waveform is still generated, and we call that a stationary waveform. So, as in the case of the guitar string, only certain waveforms are possible for the electron in an atom. So, in every single electron, in every single atom in the periodic table or element in the periodic table, there is a unique waveform per each electron in every atom. Okay? And that waveforms are limited, and this is how often all atoms are defined, or all electrons are defined in their orbitals. We can focus our attention on the waveform of varying charge intensity without really focusing at all about the actual physical nature of the electron. So we're not really studying the physical properties of electron. We're just focusing on the wave that is generated from the movement of that electron. So when it comes to studying the electron and trying to apply all these concepts of waveform and shapes of waveform and nodes and the stationary waveform, all these concepts that we have been going over. The simplest element in the periodic table where we can apply all these concepts is the hydrogen atom, simply because the hydrogen atom has only one electron in its electron configuration. So it is a lot easier to study the hydrogen, the electron in the hydrogen, than going for something like silver or lead or something with some element from the periodic table where you have over 70 or 60 electrons in the electron configuration. So we are going to focus first on the hydrogen, and that's, believe it or not, what most scientists to study to study the properties of electron decided to start with the hydrogen atom. Okay, so in general, the description of electron based on the wave mathematics for the one electron on the hydrogen atom. So all the waveform and everything that we have been talking about, it is based on mathematical calculations that are coming from the hydrogen atom, the electron and the hydrogen atom to be more specific. Okay, the negative charge is most intense as you see here, and I know this picture here is not new to you at all because we've looked at something like that when we were talking about chemical bonding. So the negative charge that you have in the center, this is the most intense in the nucleus, where the nucleus is sitting, and you have less intensity of that negative charge as you move away from the nucleus. Okay, and that's exactly what's going to generate a unique wave form for that specific electron around the nucleus of the hydrogen atom. Okay, that waveform that is generated through this electron in the hydrogen atom, it's also known as orbital. Okay, so the orbital is the place where it is most likely, or there's a high probability of finding the electron somewhere. So it is this sphere, or it is this space where the electron has a high probability of being found, probably 90% or 99% and sometimes. But again, we're not going to be able to exactly and precisely determine where the electron is sitting. So that orbital for the hydrogen atom, it is also called as the first principal energy level. Now, the first, because obviously this is the first energy level that we're talking about, and we abbreviate that as the 1s. So the 1s means it's the first principal energy level. Now, later on, we will see something as the 2s and the 3s and the 4s, because we are going from one orbital to the other, moving away from the nucleus as we have more electrons. Okay, and I think that's kind of makes sense. One of the characteristics of the first principal energy level, in addition to the fact that it is the closest to the nucleus, in the hydrogen atom, or even in any electron configuration in general, that the first principal energy level can only hold two electrons. Okay, so that sphere that we see around the nucleus, that big circle that we call the waveform, or we also call the orbital, can only accommodate two electrons. Well, a good question would be, well, what happens if there is more than two electrons? Then the electron will be positioned in an upper energy level that would be the second principal energy level, which means the electron would have a higher energy, something that we will talk about more in details. Okay, so at this point, what I would like you to pay attention to is the concept of orbitals. This is the first time we kind of understand what an orbital means, which means it is the allowed waveform where the electron can be found. So the orbital is a place where there's a high probability of finding an electron. As a result, the 1s orbital also referred to, or it's also um, um, drawn as a sphere. So if you look in any of the chemistry books, when they're talking about the 1s orbital or about the s orbital in general, will always have a spherical shape. Okay, so again, we're talking about the orbital. It is the volume within which an electron has a high probability of being found. Almost all the electron charge lies within a spherical shell with a diameter of the circle. So the shell that you see here, the spherical shell that you see here, this is where there's a high chance of finding the electron, but as you see, because the electron is really moving at a high speed. So the spherical shape represents the 1s orbital. In a couple of slides, you will also see and you will find out that the s orbital, regardless if it is the 1s, the first principal energy level, or the 2s, the second principal energy level, or the 3s or the 4s, will always have a spherical shape. That's how the s orbital exists in a three dimension around the nucleus. Okay? Well, the question that we've been trying to answer up to this point is we're trying to find out where the electron is. And we said it is very difficult, it's extremely difficult to find where the electron is. But if we assume you're able to look at the hydrogen atom and the electrons circulate around the hydrogen atom, and you try to take a snapshot of the electron, multiple pictures of the electron circulating around the nucleus, this is what you're going to find. A multiple exposure picture of the electron in the 1s orbital of a hydrogen atom might look like this, which you have a tiny dots of the electron. That is, by the way, this is a single electron. This is not multiple electron. This is the same electron, one single electron of the hydrogen atom that is sitting in the 1s orbital. So this is the electron of the hydrogen atom in the 1s orbital. But these multiple images, it tells us that this electron basically travels everywhere around the nucleus, more concentrated as we get closer to the nucleus of the hydrogen atom. Okay, less of the density of the electron, or the electron travels less frequently on the outskirts of the hydrogen atom, and it tends to be more concentrated in the center. Now, the hydrogen atom also has a second principal energy level that follows the first principal energy level. The second principal energy level has a higher energy because obviously you're moving away from the nucleus. This has to do also with the potential energy. So if you remember, if you've taken any science before, a potential energy, it is defined as how far that object is from the ground. The farthest the object from the ground, the highest the potential energy is going to be, excuse me. So the second principal energy level It is further away from the nucleus, so it has a higher energy. It has a higher energy compared to the first principal energy level. Well, in addition to having a high energy, the second principal energy level has four possible waveforms. So just like how when we looked at the first principal energy level, where we had the s orbital, correct? The waveform, the single waveform of the s orbital. The second principal energy level, things will get a little bit more complicated. So instead of having a single waveform, a single orbital, or a single shape, we have four possible waveforms and four possible shapes. So there is more room for the electron to move around. So, what are the possible waveforms for the principal energy level? Second principal energy level. Number one, there is an s orbital that exists in the second principal energy level. So, just like the first energy level, where is an s orbital, the second, there is also an s orbital or an s shape waveform. There is also a p orbital. So that is a new waveform that now we're getting introduced to. The p orbitals, it is subdivided into suborbitals. That's what we call it, the px, the py, and the pz. As we mentioned in the first principal energy level with the 1s, we can only hold two electrons in the s shape orbital. Same kind of deal with the s orbital in the second principal energy level. Only two electrons can fit in that orbital. The p orbital, on the other hand, can fit six electrons, two electron in each of the suborbitals of the p orbital in the second principal energy level. So if you add all these up together, if I add two electrons plus six electrons, so now I have opened more space to fit in more electrons. So instead of having two electrons in the first principal energy level, now I have added the possibility, or I've added more orbitals to fit in an additional 8 electrons. And that's how the electron configuration works out throughout the periodic table. Okay? Now, is there any chance that the electron in the hydrogen atom would exist in the second principal energy level? A very tiny chance. The reason for that, because the second principal energy level, it is a higher energy compared to the first principal energy level. And electrons, in order to reach a state of stability in any atom, they would look at a lower energy level. So the electron would always prefer to go to the first principal energy level, the lowest energy level possible at that time. That's number one. Number two, we are talking about attraction. Okay? So remember, the electron is negative, and you have protons that are positive in the nucleus. So if the electron moves to the second principal energy level, that means it has moved away from the nucleus, from the positive charge. So there is even less stability at that point. So the electron would definitely prefer the 1s, which is the first principal energy level. Okay, so that's in terms of the first and the second principal energy level. So what the mathematical calculation has also discovered that the 2s orbital, the s shape or the s waveform in the second principal energy level, it is actually different compared to the s orbital in the first energy level. So the average distance between the nucleus and the negative charge of the 2s electron is greater than the 1s orbital electron cloud. And that's, again, that contribute to the stability. That's why the electron will go to the first energy level. Going back to the 2s orbital, what they noticed that there is a node right in the center of the 2s orbital in the second energy level. And if you remember when we were talking about the waveform, a node means no movement for electron, or less negative charge density. So the intensity of the electron charge almost diminishes right where the node is. And that's what makes the s orbital in the second energy level. If you remember when we talked about the 1s orbital in the first energy level, the waveform looked like this. This is the wave form. And again, when we say the waveform, that means it is the orbital. In the second S, in the second principal energy level, the waveform looked quite different. There is a node in the center. So the electron at some point at the second energy level, the intensity of the negative charge, it really diminishes at some point and then it goes up back again. And that's because of the movement of the electron in the second principal energy level. Now, when you talk about the p orbitals, of course, the shape will be also different. And as you go up in the higher principal energy level, things will get even more complicated. So you can even imagine if you're talking about an atom with 65 or 75 electrons, and you can see how the mathematical calculations will get even more complicated. That's why we're only sticking with a hydrogen atom. So along with the s orbitals in the second principal energy level, right, we looked at the s, the 2s. We also have the p orbitals in the second principal energy level. And because it is in the second principal energy level, we accompany that by a number 2 to indicate that this is part of the second shell in the electron configuration. When we say the 1s, indicating that is the first principal energy level. So the p orbital generally has a quite different shape than the s orbital. When we looked at the s orbital, we said it has a spherical shape, or it has a circle if you want to draw it in a one-dimensional sketch. The p orbital, on the other hand, it almost looks like dumbbells, but it is lined up against each other in a 90-degree angle. So you will have the py sitting on the y-axis, okay, and you will have the px sitting on the x-axis, and you will also have the pz sitting on the z-axis. So you have basically 3 suborbitals of the p main orbital, that is the px, the py, and the pz. In every one of these dumbbells, there's an electron sitting there. So if I want to draw that one, there will be an electron here, there will be another electron on this one, electron here, another electron here, an electron, and another electron. So if you count all these electrons, that will give you 6 electrons in total that we can fit in the p orbitals in the second principal energy level. Now, once you move from the second principal energy level, the next one is the third energy level. And with that one, things get even more complicated because not only we have s orbitals at this point, we also have the p orbitals, and we have a new orbital that is getting introduced here, which is the d shape of orbitals. And the d shape of orbitals has 5 different suborbitals. So you can see how things are getting even more complicated. Now, as we go up in the energy level, as we open up more orbitals, we are basically opening more room to fit in more electrons. So when we do the electron configuration for the transition metals, for example, which is the metals, right, the elements in the center of the periodic table, we can use the d orbitals to fit in more electrons. Otherwise, one single energy level won't be enough. In the s orbital, if you remember, we can fit in 2 electrons total. In the p orbital, we can fit in 6 electrons, right? 2 electrons in the px, 2 electrons in the py, and 2 electrons in the pz. On the d orbital, we can fit 10 electrons because with the d orbital, we have 5 suborbitals, and you can fit 2 electrons in each. So there's 2 electrons here, 2 electrons, another 2 electrons, and another 2 electrons. So that is 2 electrons that we can fit in every single suborbital, which would increase our numbers of electrons to 10 electrons per the d orbital. The d orbital has a really unique chemistry. There's actually a chemistry that focuses only on the d block elements of the periodic table, which is also known as the transition metals. It has a very unique chemical characteristics that gives many of the metals their magnetic properties, their color properties, so on and so forth. So, but we're not going to really focus on any of that. The only part that I would like you to be familiar with, that there is a d orbital, and the d orbital can handle 10 electrons. Okay, so the 3D sublevel contains 5 3D orbitals, as I mentioned earlier. 4 of these orbitals have 4 loops whose shape is similar to the loops of the 3p orbital. So when we looked at the 3p orbitals, the p, x, p, y, p, z, 4 of the orbitals on the d has a very similar resemblance of that kind of shape. The 5th 3D orbital is shaped like a dumbbell around a donut, which is this one right here. Okay. This is how the drawing would look like, or this is how the shape of these orbitals is normally drawn. And again, most of these orbitals or more of these drawings have been discovered through mathematical calculation. So when we look at the s orbital, again, one more time, this is the s orbital, which has a small tiny spherical shape. And this is the first. This is the first. So this one is the first energy level, principal energy level. This one right here, because we have only the 1s. This one here, the 2s, this one is the second principal energy level. This one is the third principal energy level. And you can see with the second principal energy level, we are introducing the s orbitals as well as the p orbitals. And we can see the s orbital in the second principal energy level has a bigger spherical shape. When you go to the third energy level, the 3s orbital has even a bigger shape, because that basically increases the probability of finding the electron, because what happens once you go further away from the nucleus, the electron will travel away even at a bigger space. So the spherical, the orbital, the waveform will have a bigger shape to increase the probability of finding the electron. When you look at the d orbitals, definitely more complicated and more complex, as you see here with the dx, with the d squared and the dx dz and the dy dz, dx dy and the dx squared dy squared. Now, as I said earlier, in every s orbital, you can fit in 2 electrons. So there is 2 electrons in this case in the first energy level. And the second energy level, because we have the s and we have the 3p's. And in every one of these, we can fit an electron in every one of these dumbbells. And we can fit 2 electrons in the spherical. So they make it 2, 4, 6, 8. So we can fit 8 electrons in the second principal energy level. When it comes to the third principal energy level, we can fit 2 in this one and 2 of each of the suborbitals of the p orbital. So that makes it 8 plus 10 in the d orbital, because every suborbital will take 2 electrons and there is 5 of those. So in total, we can fit in 18 electrons in the third principal energy level. So we can see, if you're talking about an element, for example, with a 15, for example, count of electrons, we will need 2 electrons, we will need 8 electrons, so that makes it a 10, plus I need 5 more electrons. So my additional 5 electrons, 2 will go to the s, and 3 will go to each of these p orbitals. We will do many more examples for the electron configuration, but just to kind of give you an idea. Remember, we are talking about energy levels. So when we talk about energy levels, this is also associated with the potential energy. And I know I mentioned that earlier, that every time you have a higher potential energy, that means you have a lower stability. Okay, so for example, if you have a book that is sitting on a table, that book is pretty stable sitting on that table. But if you take that book and you try to move it up and throw it up in the air, you basically increase the potential energy because you have elevated that book into to a higher level. That elevation, that throwing the book up in the air, basically increases the potential energy and decreases the stability because the book now in the air and we're not sure what's going to happen. Same kind of concepts apply for the electrons. The electrons always look for a lower potential energy to increase their stability. Okay, so that's why they look for low energy levels when you're trying to position those electrons. So increased stability is always associated with a decrease of potential energy. For example, the 1s electron has the lowest potential energy um, compared to any of the other energy levels in the electron in the orbitals or in the shells around the nucleus. That's why the electrons will always prefer to go to the 1s orbitals first before they go to the 2s orbital because the 2s will have higher potential energy and less stable. We describe this energy difference by saying that 1s electron is in the first principal energy level and the 2s electrons are in the second principal energy level. And every time we say second principal energy level, that means we say higher energy. The first principal energy level, lower energy, means more stable. This one is less stable. Okay? So let's review some of the concepts before we dig into the electronic configuration and how we can write the electron configuration for elements and atoms from the periodic table. So we talked about orbitals, and we said orbitals essentially means the allowed waveform for electron, which would result in the shape. So we have orbitals such as the s orbital, we have orbitals such as the p, and we have orbitals such as the d orbital. The volume within each of an electron, the volume within each has a high probability of the electron being found. So that's where you find the electron with a high probability within that shape, within that waveform. Principal energy levels also called as also called as shells. So you can either refer to them as principal energy levels or as shells. The one and the 1s and the 2 and the 2s represents the principal energy level. So every time we say 1s, 2s, 3s, 4s, every number accompanies the s orbital represents the principal energy level. So if I ask where does the 4s orbital located, you should say immediately that it is located in the fourth principal energy level. Same thing for the second and same thing for the third. These sublevels, or it's also called the suborbitals, orbitals. These are the orbitals that have the same potential energy. Example for that one is the p orbital that has the x, the y, and z, and also has the same shape because when we looked at the p orbital, right, this is the pz, and this is the px, and this is the py. So all these orbitals are on the same potential, has the same potential energy, sitting on the same on this has the same size and also has the same shape. We call these the suborbitals. So the s, for example, does not have any suborbitals because the s has only one shape, which is the sphere. The p orbitals has three different suborbitals. The d has five more suborbitals, so on and so forth. Okay. Um, One of the things that I would like you to consider and also to kind of have an idea about is the Pauli exclusion principle. Well, the Pauli exclusion principle states that no two electrons of an atom can have all the same characteristics. The electrons are so unique of each other that no two electron would have the same characteristics. Okay, well, what does that mean? That means that you can't have two electrons, for example, in the helium atom that are sitting on the 1s orbital, right? Because the helium has two electrons, right? So it will be sitting on the first potential energy level, which is the 1s. So here's the sphere of the 1s, and here's the first electron. The second electron will be pointing downward. So even though this helium atom has two electrons, these two electrons are still unique to each other and they are not the same. For example, this electron here is sitting on the 1s orbital, so as the second electron. Okay? But then when you look at this one, you can see that the second electron is pointing downward while the first electron is pointing upward. So what we call it, the spin of the second electron will be different. And that's how the second electron is unique in its in its characteristics. So general electrons are described through four different characteristics. First, the principal energy level. So that one that it starts with the first principal energy level, which is 1, 2 principal energy level, 3, and it goes all the way up to 7 principal energy level. In every single principal energy level of these, there is also sublevels, which is the S sublevel, the P, the D, and the F. In the first energy, principal energy level, there is only the S sublevels, and then once you go to the second, to the third, fourth, it gets more complicated with more sublevels are added because it is more electrons that occupy every single principal energy level at that point. These sublevels, the S, the P, the D, and the F, are divided into orbitals of their own. So for example, we learned that the S orbital has always a single has always one single orbital. The P sublevel, on the other hand, has three different orbitals. The D sublevel has one, two, three, four, and five orbitals. The F sublevel has one, two, three, four, five, six, and seven. Okay, so you can imagine, for example, when you get to the E4 or the principal energy number 4, where we have the S, the P, the D, and the F at the same time, all these sublevels are filled according to their energy level with their electrons. And that basically would take us into later on into the electron configuration. So that's the principal energy level. Please make sure to kind of differentiate between the principal energy level, the sublevel, what the sublevel actually mean, and the orbital within every sublevel. The other thing that we have to also consider when we talk about electron characteristics is the spin of electron. So this is we're not going to see as much when we do the electron configuration, but when we do the orbital diagrams for the electron configuration, that's where the spin for the electron, it is going to be kind of obvious for us. Okay? So the spin of electron, as we kind of talked about it, here briefly, that determines if the electron is pointing upward or the electron is pointing downward. Okay, um, that's another characteristic of the electron. So the electron can have a first principal energy level, can be in an S sublevel, sitting in an S orbital because the S sublevel has only one S orbital, and with a spin that is pointing upward. So that's one of the identification. Well, that's an identification for one single electron. Another electron that could be sitting in the second principal energy level, sitting on a P sublevel, occupying the px orbital, and the spin of electron is pointing downward. Okay, so this is basically the identification of any electron. So that way we can give a pretty accurate and precise description for any electron in any electron configuration. Okay. So that will take us into the electron configuration. Um, the numbers, when we write the sublevels in the electron configuration, every single number represents something. For example, the number that precedes the sublevel symbol, either S, P, D, or F, this number here represents the principal energy level. And every single principal energy level always start, so principal energy level always starts with an S sublevel. So every time you see in an electron configuration, there is a sublevel of S, that means a new principal energy level has started. Okay, so the number here represents the principal energy level. The S indicates the shape of the orbital or the shape of the sublevel. So if it is an S, that means it's going to be a sphere, right? That's what we talked about, the S. It has a spherical shape, right? If you're talking about the P, so it's going to be like dumbbells on top of each other, okay? Occupying the X, the Y, and the Z axis. That's if it's an F orbital or an F sublevel. And the D, it's similar to the P, but it's a little bit more complicated. The F, you don't have to worry about. So the letter symbol, it really indicates to us the shape of the sublevel or the shape of the orbital where the electron is sitting. Okay, the small number in the on this side of the letter, that number indicates the number of electrons in the orbital. Now remember, something like an s orbital can only handle 2 electrons. Something like a p orbital, right? So s can only accept 2 electrons. P can only accept 6 electrons. This is the maximum capacity for each of those sublevels. The D can accept or can handle 10 electrons. The F can go up to 14 electrons. So how to do electron configuration for any element in the periodic table? First, what we need to do, we need to follow these rules down here. These rules are a must when it comes to writing down a correct electron configuration for elements, as we will do later in many examples. First, you have to always consider that electrons seek the lowest energy level possible. So when we start doing our electron configuration, we will always start with filling the first principal energy level. Okay, so we will fill the 1s orbital, for example. And then once we fill in all the electron, and once the s orbital has completely full, and we still have more electrons, then we will go to the next principal energy level. So that will be the s and the p orbitals. So we would fill in the 2s and the 2p with 2 electrons for the s, 6 electrons for the p, because this is the maximum capacity for what the p orbital can handle. And then once we fill in the 1 and the 2, and we still have more electrons, then we will go to the third principal energy level, which is going to be S3p. So we are going to fill our electrons again. So I will do 2s and 6p. So I filled in all my electrons. Next, I will go to the fourth principal energy level, so on and so forth. So we always start with the lower energy level possible, because that indicates a low energy means it's a stable state. So that's why the electron would prefer a lower energy level. And again, that is also connected to the potential energy, because as I said earlier, the higher you go in the energy levels, the higher the potential energy is. Okay, so with a higher potential energy, that means it's really not stable, not preferred energy level. The electron will go to the lowest energy level possible. These sublevels are filled in such a way as to place each electron to yield the lowest overall potential energy for the atom. Okay, so we will do the S and then we'll do the P in one, as I did earlier. So E2, this is 1s, 2s, and 2p. So when we have So let's say that we are trying to do electron configuration for an atom with two, four, with six electrons. Okay, so that would be the carbon. So with two electrons on the first principal energy level on the s orbital, I still have four more electrons. So the next one will go to the s orbital up here. When I go to fill in my next electrons, which is two electrons, this will go to the p orbital again because the s orbital within the second principal energy level, this guy here has low potential energy compared to the p orbital, because even within the principal energy level, the s orbital or the s sublevel will come first and the p would follow. So we will fill in the s orbitals first. No two electrons, no two electrons in an atom um, can be the same in all ways, as I said earlier. So if the electron is sitting in the same principal energy level, it is sitting in the same sublevel, in the same s orbital, for example, the Pauli exclusion principle dictates that this second electron has in some way be different than the other electron that is sitting with him or sharing the same orbital. In this case, for example, will be the spin of that electron. So that accompanied electron sitting on the same orbital, on the same principal energy level, is pointing upward. The second electron that is coming to sit on the same orbital will point downward. So that electron will have different identity than its buddy that is sitting in the same orbital. And then again, that is the Pauli exclusion principle. So if someone asks you what is Pauli exclusion principle, that means no two electrons in the same atom can have the same identity always. Electrons has to be different in some shape or form. When electrons are filled, so when electrons are filling orbitals of the same energy, they prefer to enter the empty orbitals first, and all electrons and half-filled orbitals have the same spin. This is called the Hund's rule. Okay, so this probably does not apply to the s orbital because the s have only, or the s sublevel, because the s sublevel has only one orbital. But something when you're talking about the p sublevel, which has three different orbitals, the px, py, pz. So let's say that you have three electrons left that are going into the p sublevel. Okay, so the way these electrons are going into the p sublevel, and instead of going as one, two, three, the electrons, they would like to sit alone by themselves in every single orbit of this, unless if they have no other option. So if there is a room for these electrons to be alone, sitting in every one of those orbitals, spinning in the same direction, that would be the ideal case scenario. So for the three electrons, they would like to be kind of independent, sitting in their own orbital. So they would go like this. Okay, so electrons will go a singlet or a single electron sitting in every single of those orbitals, pointing in the same direction, pointing upward. Okay, so let's say, for example, you have four electrons that is going into a p orbital, for example. So in this case, you will distribute your electrons, a single electron in every single orbital pointing upward, and then the next electron that comes in will be pointing downward. It will have a different spin direction because electrons sitting on the same suborbital pointing in the same direction, same spin, it doesn't happen because that electron here, if you put that one upward, for example, beside it's mathematically not possible, chemically and physically not possible, this will result in two electrons having the same identity, which really stands against everything Pauli stands for. Okay? So electrons will start at a single electron in every single suborbital pointing upward, and then you'll start coupling these electrons if you start adding more into every one of those suborbitals. I think when we do more examples, you guys will have a better idea for this. Again, continuing with writing electron configuration, you have to determine the number of electrons in the atom from its atomic number. So when you look at any element, you'll have to locate that element in the periodic table. And I will be giving you a special periodic table that is dedicated toward writing electron configuration. And I will be also giving that one during the exam. So I don't want you to really stress out about this. I promise it's going to be as easy as you think. Um, so you'll have to locate that element on the periodic table, and then you'll have to see where the atomic number is, because with the atomic number tell us number of electrons, correct? Because a neutral atom will have the same number of electrons as number of protons. So something, for example, like nitrogen, which is 7 protons, because we're talking about the neutral nitrogen, that means it is 7 electrons as well. So you will use the 7 count of electron to write the electron configuration for nitrogen. Okay, now what we need also to factor in that sometimes we might be writing electron configuration for cations and anions. So if we are talking about, for example, the electron configuration for nitrogen 3 negative, that means 7 electrons from the periodic table based on the number of protons, and then you'll have to add the other 3 electrons, so that makes it 10 electrons total, right? Because nitrogen in this case has accepted 3 additional electrons, so we have the 3 electrons that we have to write the electronic configuration. Okay, so that makes it 10 in total. If you're trying to do something for calcium, which is like 20, so for calcium, 20 electrons, number of protons equal the number of electrons for a neutral atom. But if you are trying to write the electron configuration for a cationic calcium, which is 2 positive, that means instead of writing 20 electrons, you'll have to write the electron configuration for 18 electrons for calcium 2 plus, because calcium has lost 2 electrons. Okay, and we will do some examples for this one as well, but I want you to keep that in mind. We don't write electron configurations for neutral atoms. We do also for ions, either cations or anions. So determine the number of electrons of the atom in the periodic table based on the atomic number. Okay, so if you can't really do this one, I don't see how you will be able to write the correct electron configuration. So first, locate your element from the periodic table. Once you do that, then you'll have your number of protons, hence number of electrons, and that's how you can write the electron configuration. Add electrons to the sublevels in the correct order of filling them from the beginning of the periodic table until you reach the element you are describing. And then you have to remember that electrons in each sublevel, 2 electrons in each S sublevel, 6 electrons in P, 10 electrons in D, and 14 electrons in the F sublevel. Okay, so before going into my special periodic table to do the electron configuration, I would like to go over the periodic table quickly, because I know we have been using the periodic table mostly for, referring to properties of element, metals, non-metals, especially in the beginning when we were talking about bonding and stuff like that. But it turns out that the periodic table is actually divided into different blocks. So if you look at this periodic table here, all the elements that you have that's sitting on this side of the periodic table, which is a group 1 and a group 2 in the periodic table, this is known as the S block of the periodic table. Okay, well, what does the S block in the periodic table mean? That means all the electrons that is sitting in the S block in the periodic table, their electron configuration will finish with an S orbital. So now if I sit now and try to do any electron configuration for the calcium, magnesium, sodium, so on and so forth, the last sublevel you're filling, or the last sublevel will be filled, is going to be an S orbital or an S sublevel. That's why it is referred to as the S block elements. The D block elements is the same thing. All these elements in the D block, their electron configuration will finish with a D sublevel. So the last electron in these electron configuration will be located in a D sublevel. That's why it is referred to as a D block element. Same case scenario with the P block elements. All the elements in the P block will finish their electron configuration with a P orbital or P sublevel where the last electron will be sitting. Same deal with the F block. Okay. So these are the type of sublevels, either the S, the P, the D, or the F. The number of orbitals within every one of these. I think at this point I may sound like a broken record because I know we've talked about this so many times. S has 1 orbital, P has 3, D has 5, F has 7. Capacity, maximum capacity of electron or maximum number of electrons every one of those sublevels can handle. S will take 2, P 6, D 10, and F 14. Okay. So this is the long periodic table, and this is not the classical periodic table that we have been looking at since the beginning of the course, or any periodic table that you will see in another book. You will use this periodic table for electron configuration only. So you will only use this electron configuration, this table to do the electron configuration. Okay, you're not going to be using it. Obviously you can get the atomic number and other stuff, but you're not going to use it for any other application. This is only for electron configuration. That's why I refer to as the long periodic table. Okay, so what we do when we try to do the electron configuration, as I mentioned earlier, first you need to locate your element that you've been asked to write the electron configuration for. All right, let's do an example for the iron and try to put everything that we just talked about in application. So Fe26, first what I will do is I'll try to locate Fe iron based on its atomic number on my long periodic table. And I can see it right here in the center of the D block of the periodic table. You have to keep in mind that every squared in every block of the D, the P, and the S indicate the capacity of holding electrons. So that's why when you look at the S block, there is 2 little squared boxes. Once you reach a third electrons, you will have to go to the P orbital in this case. The P will have 6 different squared, which means the capacity of holding 6 electrons. Once you go above 6 electrons, what you will need to do is you'll have to go to the 4th principal energy level. Once you reach the full capacity of the 4s in the 4th principal energy level, then you'll have to go and move along to the d orbitals to fill in the next orbitals, empty orbitals available. Okay, that's why when you look at the s block, when you look at the p block, the d and the f, for example, for the s you have 2 little squares indicating 2 electrons. For the p there is 6 different squares indicating 6 electrons. D is 10, F is 14, just in case if you wonder where all those squares actually represents. So first what we did is we located the iron right in the middle of the D block of the long periodic table. What I would like also to do is I'd like to kind of indicate my principal energy level. So I have the 1s up here, so this will be first principal energy level. And these 2 squared will represent the first principal energy level, correct? Because we can handle 2 electrons with the s orbital. With the 2s, this will be my second principal energy level. And we can see with the second principal energy level, we have the s, we have the 2s as well as the p. So once I fill all the s orbitals, I'll be going to the p block in the periodic table. The 3s, same deal as the 2s, and we have the 4. All right, my 3 is a little bit big. That's my 4th, my 5th, my 6th, and my 7. Okay, so when we are filling electron in this long periodic table, the way we're going left to right. Okay, left to right, and then once we reach the end of this side of the periodic table, and you still have more electrons, still have more electrons in your electronic configuration, what you need to do is you need to make a loop. and start again on the next principal energy level. Okay, let's do an example with the iron and see exactly what that means. So for the iron, it's Fe26. I'm gonna put a circle around iron in Fe26, and you can also do that when you're doing your own electron configuration. And we can see that I can write Fe26. Always write the name or the symbol of the element, and below it the atomic number indicating the number of electrons that you'll be writing for the electron configuration. So since we have 26 electrons sitting in the D block, that means the 1s, the first principal energy level, has been already filled, right? Otherwise, we will not be sitting at the D block with the 26 electrons. So that makes it 1s2. And I can see the s orbital is already filled because we are going all the way down to 26 electrons. So that makes it 1s2. So the first principal energy level with 2 electrons. I have reached the left or the end of my long periodic table. Now what I need to do is I still have more electrons going. I need to reach all the way down to 26 electrons. Then what I will do is I'll make a loop and I will start with the second principal energy level. My second principal energy level is 2s2, correct? It is already full because I have not reached my golden number of 26. I'm going to keep going this way. What is the next one that I hit here? Is the p orbital. What is the number? It is a 2p, so that makes it a 2p6. It's all full, correct? Because I still need to go down all the way to 26 electrons on the D block. So I've reached my end on my long periodic table. What I need to do is I need to make another loop and start with the 3s block and the periodic table, so that will make it 3s2. Again, why it's full? Because I'm still going into my 26 electrons down here. Once I reach my 26 electrons, then I'll have to stop. And if it is partially full, it is partially full. It is full orbital, it is full orbital at that point. But since I have not reached my 26 electrons for the iron, all the previous sublevels or the previous orbitals are full to maximum capacity. Okay? So that makes it 3s2 with 3 electrons. Next I have is the 3p. And again, guess what? This is also full to maximum capacity. So that makes it 3p6. I'm still not at my 26 electrons. So what I need to do is I need to start again from the other end of the periodic table on my next principal energy level, which is the 4s. So that makes it 4s2. Now what next comes after the 4s orbital is the 3d block. So I'm going to write 3d. And next I have 1, 2, 3, 4, 5, 6 with 6 electrons. Okay? And now I stop. I cannot really continue because I have reached my maximum number of electrons for iron, which is 26 electrons. This one here, this represents the electron configuration for iron, for neutral iron. Again, we can deal with cations and anions. Things will be a little bit different. Okay? So as long as you follow and as long as you use the long periodic table version for the electron configuration, I think it's pretty sure it's pretty straightforward. And I'm sure it's not going to be that complicated. Okay? Let's do another example. Let's do one for, let's clear everything. And let's do one for the sulfur. So sulfur is 16 electrons. So first what I need to do is I need to locate sulfur with 16 electrons on my long periodic table. It's right here, 16 electrons. This is my first principal energy level. This is my second, my third, my fourth, my fifth. I don't think we'll be reaching the fourth principal energy level anyway, so I'm going to stop right there. So in order to come all the way down to 16 atomic number on the P block, The first principal energy level, the 1s2, is already full. The second principal energy level is also full, along with a 2p. So what is the next one that I'm hitting on my arrow when I'm moving from left to right? It's the 2s with its 2 electrons and the 2p6, because I've reached the end of the p block, indicating I have filled all the p block with electrons. Okay, the next one that I have here is going to be the s orbital. So that is going to be a 3s2. I have not reached my 16 atomic number on the p block. So this will continue down this way. So how many electrons I have in the 3p orbital? I have 1, 2, 3, 4. So that is 3p4. Okay? You can always indicate your energy levels if you make a backslash like this. That means this is the first, this is the second, this is the third principal energy level. Now, if you do the count, this is 2, 4, 10, 12, 16 electrons. Okay? You don't have to do these backslashes, but just in case if you're curious where the energy levels are. Let's do another one. Let's do the gold on this. Let's do an example for the gold. So for the gold, it's 79 electrons. So that's going to be way below on the periodic table. And if you look here, this is where the 79 gold is located. What does that mean? That means all the sublevels, all the orbitals prior to that, the 1s, the 2s, the 3s, the 3p, the 4s, all these sublevels are full to maximum capacity with electrons until you reach the 9th electron on the d suborbital. That's where you stop. Okay, that's number 9 right here, because 1, 2, 3, 4, 5, 6, 7, 8, 9 electron. Okay, so your d sublevel, when you do the electron configuration for gold, technically should have 9 electrons at the end. Let's see how that one is going to look like. So this is my first principal energy level, the 1s. This is my second, my third, my fourth, fifth, sixth, and seventh principal energy level. Okay, so I'm starting with the 1s right here. So for gold, 79, the 1s2 is full with electrons. I'm going to keep going on my long periodic table. This is the 2s. This is the 3s. This is the 4s, I'm sorry. This is the 5s. And this is the 6s, 6th principal energy level. So I'm going to write all these sublevels filled with their electrons until I reach the 5d sublevel. And that's what I have my 9 electrons at the end. So will be 1s2, 2s2, correct? So these are full with 2 electrons. And 2p6 is also full with 2 electrons right here. Now I have 3s2. And I have the 3p right here is also full with electrons. So now I have reached all the way to the end. I'm starting with a new principal energy level, which is the 4s2, right? So this is 4s. That's what I'm starting with right here. So 4s is full with electrons. What comes after the 4s is the 3d block, or the 3d suborbital. So 3d, but as you see here, the 3d is full with electron because we're traveling all the way to the end of this periodic table, or this period in this periodic table. So this will be 3d10. What comes after the 3d? This will be the 4p. Is it full with electrons? Yes, it is full with electrons. 6. All the way to the end of this one. So next I have is the 5s, which is down here. So 5s with 2 electrons. What comes after the 5s is the 4d, which is right here, if you've lost track of me. So this is 4d, and that is going to be 4d10 electrons. All the d electrons on this period is full to maximum capacity, right? Because we're still going all the way to the end. What comes after the 4d? It comes the 5p. So that's going to be 5p6. It's also full with electrons. So I've reached the end of the 5p on this side of the periodic table. Now I'm going to the next period, and the next one is going to be the 6s. Is it full to capacity with electrons? Yes, it is. 6s2. As long as you're crossing all the block, as long as you're crossing that block when you're moving across the periodic table, that means the electrons, it is full to maximum capacity with electrons. Now the F that follows the 6s, that is going to be the 4f. As long as I'm traveling all the way to the end of the 4f, that makes it 14 electrons. That's the maximum capacity for the F. If you are unsure, you can always count the boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and 14. Now the next one I have is the 5d. And with this one I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is the electron configuration for gold. Applying all the rules that we just looked at. And again, if you're using the long version of the periodic table, that's I think that's fairly easy. So sometimes instead of writing the complete electron configuration, just like how we did with something like gold, which really takes a long time going from every row to the next row on this long periodic table, writing all these sublevels, which is kind of irrelevant to any chemical interaction, because chances to get electrons from the from the 1s2, chances to get electrons from the 1s2 orbital or the 2s2 orbital, or even the 2p6, any of these electrons to get involved in any chemical interaction, it's just not likely to happen. What we focus as chemists, and as you know at this point, that we only pay attention to the electrons at the highest energy level, or what we also refer to as valence electrons. These are the electrons that are in fact involved with losing, gaining electrons, forming bond, breaking bonds, so on and so forth. So in our abbreviated electron configuration, we are going to really focus on the last electron sitting on the outer, on the last orbital in the electron configuration. Since we're talking about a group of gases that are a group of electrons that are really not involved in any chemical interaction, we will use the noble gas configuration to represent these electrons, because they are really not important for any chemical bonding. We often describe electron configuration to reflect this representing the noble gas electron with a noble gas symbol in bracket. So what we will do is we will abbreviate all these count of electrons that are really irrelevant to chemical interactions, and we substitute that to what is equal to the electron configuration of a noble gas. We will do an example shortly. For example, if you look for the sodium, which is 11 electrons, what we can do is we can use neon, which has 10 electrons, right? If you go back to the periodic table, let's find a good one. So this is where neon is sitting, with 10 electrons, and what I can do is I can simply just move to the second principal energy level, which is the third principal energy level, and with 11 I can just use a 3s1, okay? And that's what I will do. So if you go back to the abbreviated format, I have substituted all these 6 electrons with the electron configuration of neon, which is 10, and then I just add the 3s1 at the end, because the 3s1, or the electron in this third principal energy level, and the s sublevel, that's the only electron that we really care about. That's the electron that the sodium loses to become a sodium 1+, the oxidation number for sodium. Okay? So we will essentially do the same kind of principle to all electron configuration in the periodic table. So how do we do abbreviated electron configuration? First, you'll have to locate that element in the periodic table, similar to what we did to previous examples. Then you write the symbol in a bracket for the noble gas that was preceding that row in the periodic table. Okay, so you would look at the periodic table, locate that element, look at the preceding row on the periodic table, and take that noble gases to represent the electrons that are not involved or in the inside of the electron configuration. Okay, so next, move back down to the row containing the element you wish to describe. Following the elements of the row from left to right, write the outer electron configuration associated with each column until reach the element you are describing. All right, let's try to do a practice problem using the abbreviated electron configuration. First, we have the strontium, which is 38 atomic number. So first, let's locate strontium on our periodic table, which is going to be down here. What is the noble gas that precedes this row of the strontium on the periodic table? 38, I have 36. That's the last noble gas that comes before the last electron, the row of that element on the periodic table. Okay, so we have 36, which represents krypton 36. Okay, so if I want to write the electron configuration for strontium, which is 38, I will say krypton bracket, that will be 36 down here. And then what follows krypton 36? I have the 5s as you see here. So that is going to be 5. Oops. So that is going to be 5s1 2. 5s2. Because both electrons are in the 5s on the 5s orbital or the 5s sublevel. So this is the abbreviated electron configuration. Or it's also called the noble gas electron configuration. All right, let's try another one. Let's do the germanium. So first what we need to do is we need to locate germanium on the periodic table, which is 32. That is going to be right in the P block, on the 4p if I want to be more specific. Okay? Next, I need to see what is the noble gas that precedes that row on the periodic table, and that is going to be 18. And 18 for noble gas, that represents the argon. So when I write the germanium electron configuration, and instead of writing the 1s2, the 2s2, the 2p6, 3s2, 3p6, so on and so forth, I can replace all this by saying AR18. Okay, next I need to see what is the next orbital that that follows that electron configuration, or we go back to the beginning of the row where that element is being located. So we have 4s2, right? Because both are full. Next, I have the 3d, so that is going to be 3d. Do I have the 3d all full? Yes, because I am going all the way to the end of the 4d, so that's going to make it 3d10. Now, next, I have only 2 blocks in the p block, so that makes it 4p2. So that's for the germanium. Okay, how did I know it is a 4p? Because it does say 4p on this block in the periodic table, on this periodic table. Let's try to do another one. Let's do titanium, Ti81. So can you imagine writing the electron configuration for Ti81? That would probably take me at least a couple of minutes just using this long periodic table. And again, this is only tailored to you guys, so it make it easier for you to write the electron configuration. But generally, when people write the electron configuration, this table does not exist. People will have, chemists will know how to write all these sublevels based on their energy levels. Okay, so titanium, which is Ti81, 81. So when I look at the titanium 81, I need to locate 81 first on the periodic table, which is down here. Okay, what is um what is the noble gas that precedes the 81 on the row before that one? It is the 54, and 54 is xenon. So instead of writing all these rows before getting to the 81, which is down here, I can essentially say xenon 54. And then from 54, I'll continue my count. So 54, what comes after 54? We have the 6s that comes after the 54. So that is going to be a 6s. Is it 2 electrons, 1 electron, 4? We can't have 4. It's an s. It must have a 2. And it is going to have a full count of electrons because we are going across the s block. What comes after the s or the 6s? We have the 4f that comes after that. Is it a full house for electrons? Yes, it is going to be a full count of electrons. 4f14. What comes after that? It's the 5d. Is it a complete count of electron? Yes, as long as we're going across the whole block, that makes it 4d10. What comes next? We have the 6p. How many electrons? I have only 1 electron because this is how far we moved in the p block. So this is what we call either, like I said, either the abbreviated or the noble gas electron configuration. In the exam, you will have both flavors. So I will ask you to write both the complete electron configuration and the noble gas or the abbreviated electron configuration. So try to be familiar with both. When it comes to ground state and excited state, waveform can change from 1s shape to 2s. That means electrons, we can change the location of electrons from 1s to the 2s. And that happens from adding electron, from exciting these electrons by adding more energy or targeting these electrons with energy, which makes these electron absorb that energy and then travels or goes from one level to the next level. Okay, so the energy is elevated from being a first principal energy level or from being a 1s shape to a 2s shape. We say that electron can be excited from 1s orbital to the 2s orbital. Hydrogen atoms, for example, with their 1s orbital are said to be in their ground state. So the electron, when we write the hydrogen atom with their 1 electron and we say 1s1, this is considered as a ground state because the electron is sitting what it's naturally is supposed to go on the lowest principal energy level, which is the 1s1. We can alleviate that or move this electron from the 1s1 to the 2s to the 2s or to the second principal energy level by adding energy to the hydrogen atom. So it will be in the 2s1, but this is an excited state, okay? And it is considered an abnormal state for the electron configuration for the hydrogen, okay? And the electron will eventually lose that energy, emit that energy, generally comes through light, and returns back to the ground state to where it naturally is supposed to go. So hydrogen atom with its electron in the 2s orbital is an excited state. So how do we determine what is an excited state and what is a ground state? Okay. So in order to determine which one is a ground and which one is excited, we look for abnormalities in the electron configuration. Any abnormalities in the electron configuration indicating it is an excited state and it's not a ground state. Okay, so let's look at the first one here. We have 1s2, 2s2, 2p4, and 3s1. But we have talked about this so many times at this point that we know that when we're filling the electrons, electrons would like to go on the lower sublevel, on the lower energy sublevel, then it will go to the next principal or the next sublevel in energy. And we know that the p orbitals always accept 6 electrons, correct? But we notice in this case that P has 4 electrons, and the S, the next principal energy level, the 3s, has an electron. So to me, it seems like one. Wait, let's delete this one. To me, it seems like one of the electrons on the p orbital, what is supposed to be sitting along with its buddies in the p orbital, has been excited to move to an upper energy level, to the next sublevel, and occupy the s orbital. Does that make sense? Because ideally, what this one should look like: 1s2, 2s2, 2p5. And the 3s, oops, and the 3s will have 0 electrons. But what happened here: 1s2, 2s2, 2p, one of those electrons were excited and took a new position in the S sublevel, in the third principal energy level. Okay, which is really what we normally expected, because we know that the p orbital, before going into the 3s orbital, the p orbital in the second principal energy level has to be completely full to maximum capacity with 6 electrons before starting going into the 3s orbital, correct? Which means that this electron on the t orbital has been excited, gained more energy to go and start and to go and position in the third principal energy level. So this one is an excited state. Okay, let's look at the next one. So the next one we have is 1s2, 2s2, 2p4. Do we see any abnormalities in this electron configuration? Not really, because we know that the s orbital can only accept 2 electrons, and that's where the 2 electrons is sitting. The p is accepting 4 electrons, and it is as expected, because the p can accept maximum of 6 electrons. It has 4 electrons. None of the electrons is going to an upper principal energy level with half full or partially full orbital prior to that. That means this is a ground state. On the next one here, the 1s2, 1s1, and we have a 2p5. Do we notice anything abnormal with this electron configuration? Yes, we do, because the 2s orbital, this one should be at 2s2 maximum capacity. But what happened here, one of those electrons was excited and positioned along with the p electrons in the 2p sublevel, and that is an excited state, because what this electron configuration should look like: 1s2, 2s2, 2p4. But what happened with an additional energy, the electron on the 2s orbital absorbed that energy and traveled from the 2s to the 2p, resulting in a 2s1, 2p5. So this one is an excited state. So how do you determine if it is a ground state or an excited state? You look for partially full orbitals against to what we have been talking about in terms of Hunt rule, Pauli exclusion principle. Once you see any electron configuration that does not conform with any of the rules that we went through, that means it is an excited state. If it doesn't, that means it is a ground state. It is a stable electron configuration. Now, any of these excited state, the electron really won't last in these orbitals. Like, for example, in this case, the electron from the s orbital that went to the p will not really last in this higher principal energy level for a long time, because electron would like to go back to the ground state, to the stable electron configuration. So electron will eventually return there with emitting energy that generally comes out as light. Okay, so that's in terms of ground state and excited state. Please pay attention to this. So with orbital diagrams, what the orbital diagram is, basically, it is another way to represent the electron configuration. So generally, you can't really do orbital diagram without completing the electron configuration. With the orbital diagram, it really dissects the electron configuration. It tells us exactly where the electron are sitting, if it is either in a px or py or pz orbitals, or suborbitals, I should say. Same thing with the d suborbitals. Um, the diagram, as we will see later, also tell us how the electrons are spinning. Is it upward or downward? So it is definitely more in depth, electron version of electron configuration, and it is really helpful for scientists to look at orbital diagrams, because it gives a better idea to understand some chemical properties and physical properties as well. Okay, so chemists sometimes draw orbital diagrams such as the following with lines. So the way we do it is we do lines representing the orbitals, and we do arrows that represents the electrons. Always when we write the orbital diagram, and that's a really common mistake by people that I've seen throughout the years, uh, you need to make sure that when you're writing your orbital diagram, you're starting with a lower energy first, and the highest energy that comes next. So we start with low energy and then high energy. We always go from bottom up when you're writing the orbital diagrams, indicating the higher energy of each of those orbitals. So the 1s starts first, the 2s comes next, the 3s follow, the 4s comes next, so on and so forth. Okay. Some people, they would make a mistake and they would start always with a high energy at the bottom. So they will start with the 7s and then the 6 and then the 5 and then the 4. That is incorrect. You always start with a lower energy, as we will do in examples in a second. Okay. Um, so the line representing the 2s orbital is higher when we do the orbital diagram, indicating it is high potential energy. So it's not arbitrary it's not arbitrary when we're doing all these lines. It basically represents the potential energy for these orbitals. What you see here, this is the orbitals for ground state of any element, and when you see here, this is the 1s, for example, the 2s, and the 2p, and then it follows by the 3s, 3p, 4d, and then the 4s, the 5s, the 6, the 7, etc. Okay? Now, beyond that, it's not really necessary for you to try to do the orbital diagram. I think this is plenty to work with. Orbital diagram shows the distribution of electrons and the possible orbitals and the relative spin of each electron. So, as I mentioned earlier, when we are doing, for example, 1s2, 2s2, 2p3. So when we look at this electron configuration, we can't really tell how the three electrons are positioned. Is it upward? Is it downward? Is it sitting in the X, in the Y, in the Z? We don't really get any of this information, but we can tell that it is sitting in the last electrons are sitting in the p orbital in the second principal energy level. With the orbital diagram, we can see the electron sitting in every single orbital. We can see where the electron is pointing. Is it upward or downward? And that's what the orbital diagram gives us. How can we do orbital diagrams? First, you draw lines for each orbital of each sublevel mentioned in the complete electron configuration. So as I said earlier, without doing the electron configuration, you can't do the orbital diagram. So even if I ask you in the exam to do the orbital diagram for such and such element, please do the electron configuration first. It makes it a lot easier. Then you draw and label one line for each S sublevel, 3 line for each P sublevel, right? Because when we talked about the P orbitals, we said there is suborbitals of 3, the px, the py, and z, 5 for the d, 7 for the f. For orbitals containing 2 electrons, what we do following Hund's rule, or even the Pauli exclusion principle, we draw one arrow up and one arrow down, indicating electrons at opposite spin. You can't have electrons with the same direction pointing in the same direction in the same orbital. For unfilled sublevels, we follow Hund's rule. So we start with single filling of electrons, and then we go back and couple the electrons in the opposite side of spin. So let's do the orbital diagram for iron, which we just did the electron configuration. As you see here, the electron configuration is right there, and without that, we're not going to be able to really tell exactly how many orbitals we have and what are the energy levels that are going to be there in my orbital diagram. So first, what I will do is I'm starting with the 1s at the bottom of my page. So always start with the lower potential energy orbitals at the bottom of your page. Next we have is the 2s. Along on the 2s, on the same energy principal energy level, I have the 2p as well. And that is going to be 1, 2, 3. Correct? Because we know that the p orbital has 3 different or little suborbitals, and every one of these is the px, the py, and the pz. I don't expect you to write the suborbitals symbols on the p orbital, but it's just to indicate to you what every single line of these represents. Once I have the 1s and the 2s, the next one I have is the 3s, or the third principal energy level. So this one I have 1 because the s always has a 1 single suborbital. And then on the 3s, also on the third principal energy level, I have 3p as well. And that is going to be 1, 2, 3. Same deal, px, py, and pz. In the same time, I have also a 3d, right? Because the 3 here represents the principal energy level. So I need to make sure that all my orbitals with the same principal energy level, they go on the same level on my orbital diagram. So in this case, I have the 3d. How many lines I have for the 3d? I have 5. 1, 2, 3, 4, and 5. Next, what I have the 4s right here. So this is going to be my 4s. How many lines I have for the 4s, or how many sublevels for the s orbital? That is only one sublevel for the s orbital. Okay? So now what I need to do is I need to start filling my electrons. How many electrons I have on the 1s? So that is going to be 1. All right, let me color code things, make things a little bit pretty. Okay, so on the 1s2, I have 1 electron pointing upward and second electron pointing downward. On the 2s2, I have 2 electrons. Same thing, 1 electron pointing upward, second pointing downward. On the 2p6, I have 6 electrons, but I would like you to get in the habit of half filling the suborbitals before going back and coupling the additional electrons. So what we do with the 2p, since I have 6 electrons, we start with single electrons. Do I have more electrons on the p? Yes, I do. Second wave of electrons will be coupled downward, indicating an opposite spin for that electron. All right, now we're up next to the third principal energy level, which is 3s2. How many electrons? 2, 1, 2. For the p3p principal, or the 3p orbital, I have 6 electrons. So that will be 1, 2, 3. That's a 3. The next 3 is going to be opposite direction. All right, let's do the 3d orbital. On that one, I have 6 electrons. So what we do is we start with single electron following Hund's rule. 2, 1, 2, 3, 4, 5 electrons. But I have 6 electrons. So the 6th electron, we are starting again a new count. So this will be on the first, going back on the first suborbital for the d, and that is going to point downward. Make it a green. So this one is going to point downward, okay? So if you were to write, because I have seen people making common mistakes, 1, 2, 3, 4, 5. This is for the 3D. Some people, instead of writing 6 electrons for the D in this format, what they will do is they will do 1, 2, 3, 4, 5, 6. And that is incorrect because you still have 2 electrons that are not filled. This is extremely unstable if it actually were to happen in real life, when it comes to the electron configuration. Atoms, all electrons will always go alone in every single suborbital, but then you will go back and couple in opposite direction of spin. So please do not make this mistake. So now I have filled my d orbitals. Next, but last but not least, is the 4s, and that one also has 2 electrons. Okay, so that will be 1. Oops. One and 2. So this is the orbital diagram. For iron. Let's do another practice for the orbital diagram. Now, let's do the orbital diagram for sulfur. First, what we do, just like how we did with the iron, we need to write down our lines representing the orbitals for this atom. We're starting with a lower principal energy level first at the bottom of the page. So this will be 1s. Next, what I have the 2s. So this is going to be 2s. And again, on the same principal energy level, I also have 2p. Has the same, because remember, when we say 2p, this one represents the principal energy level. So all the 2's has to be together on the same level when you're doing the orbital diagram. So this one is going to be a 2. Let me clear this one up. This one is going to be 2p. 1, 2, 3. Because p has px, py, and pz, 3 suborbitals. The next one I have is the 3s. So 3s. So it's going to be 1 orbital, suborbital, and 3p. 1, 2, 3. And that should be it. Now what I need to do is I need to distribute my electrons. With the 1s, one pointing upward, second pointing downward. The 2s, upward, downward. With a p, 1, 2, 3. Is it a full count of electrons on the p? Yes. The next will point downward. Next, I have the 3s2. 2 electrons, one upward, second downward. Next, I have the 3p with 4 electrons. So first, I'm going to start with single electrons in every single orbital, and the 4th electron will go down and couple. So that's how we have 4 electrons on the 3p. Common mistake. People will do something like that. With the 3p, instead of following the Hund's rule and the Pauli exclusion principle, what they will do is for 4 electrons, they will do 1, 2, 1, 2. And again, that is incorrect. Similar to the D scenario that I just talked about. This is extremely not stable, and it does not happen. You start with single electrons, and then you go back uncoupled. So this is examples for the orbital diagram. You need to have a correct electron configuration in order to have the correct orbital diagram. Common mistake, people will always start with the, will not start with the correct principal energy level from the bottom of the page, indicating the potential energy, and people not following Hund's rule when it comes to coupling the electrons. Please pay attention to these, and I think you'll be fine if you do. So with these 2 examples, what the orbital diagram help us understand, as I said earlier, it really shed the light and gives us a better idea to see where the electrons are positioned, and how we can steady electron in a better way in general. What you see here, this is a more complicated way of representing the electron configuration, or the electron, where the electron is sitting in the orbitals. This is just for the first and the second row on the periodic table. So if you see for the hydrogen, for example, where hydrogen has only one s, you can see the electron is sitting in the 1s orbital. When you go move along to the next one, which is the helium with its two electrons, we are still talking about the 1s orbital with two electrons, one pointing upward, second is pointing downward. Things get a little bit more complicated once you move to the second row of the periodic table with lithium. With lithium, we have the 1s orbital that is full with two electrons that is pointing up and down, as you see. And now we have the 2s orbital, which is a bigger in shape, a bigger spherical shape compared to the 1s. That's why you see it bigger in the background with a single electron pointing upward. Moving to the beryllium, still it is the 2s because we can still add more electrons, and it's pretty much s orbital, small s-shaped orbital, the 1s with the 2s and two electrons, one pointing upward, one pointing downward. Now the boron, we are now introducing the p orbitals. So we have the 1s in the center, we have the 2s, the big orange globe in the back, and now we have the px orbital that is introducing itself to us with one electron pointing upward. Now we have, when you go to the carbon, now we have the py orbital. Now we have with the electron pointing upward. With the nitrogen, now we have the pz orbital with the electron pointing upward as well. Because again, when we talked about distributing these electrons, we always go a single pointing in the same direction, and then we go back and pair them or couple them with electron pointing downward. Now with the oxygen, now we are still using the the 2p orbital, but electrons are pointing downward with the second electron coming in. As it keeps moving along, now we have you have the fluorine, and you have the neon. That's why it's easier for us to draw lines than being very creative and being artistic and try to write all these orbitals and globes. So common mistakes. I think if you kind of try to pay attention to this and try not to make this kind of mistakes, you will be totally capable of doing electron configuration. First, the complete electron configuration. People would generally make mistakes by counting or miscounting the count of electrons. And that comes from incorrectly locating the element on the periodic table. So please make sure when you're locating that element on the periodic table, you are locating the element with the correct atomic number that you've been asked to do the electron configuration, okay? Another mistake that people will be using the regular periodic table instead of using the long periodic table for electron configuration. That will give you the incorrect electron configuration as well. When it comes to orbital diagrams, and I can almost guarantee you some people will still make that mistake, that when you are writing the potential energy, when you're writing the orbital diagram, you need to consider the potential energy when you're displaying these lines, these orbital diagrams. So when you're writing the 1s and the 2s orbital, make sure that you're not starting from the top of the page. So some people, I know they will still do 1s, 2s, and they will do the 3s, and that is incorrect. Remember, when we do the orbital diagram, we always start from the bottom of the page with the lowest principal energy level. So we start with the 1s, and we start with the 2s next, and then we do the 3s, right? And we do the 4s that comes next, and then so on and so forth. So you have to start from the bottom of the page, making your way up, indicating the lower principal energy level at the bottom of your orbital diagram. Number two, when it comes to orbital diagram, people forgetting to leave electrons unpaired with the same spin when adding electrons to the p, d, or f orbitals following Hund's rule. And that what basically means that if you have a partially filled orbital like the p, the d, or the f, you need to start with single electrons in every single orbital, and then you go back and pair them or couple them with opposite spin, opposite direction spinning electrons. Okay, so these are the common mistakes. If you please pay attention to this, I think you shouldn't have any problems doing the orbital diagram or even doing the electron configuration. Well, the next question, I'm assuming once you have listened to this lecture, went over all these details, why is this matter? How is this relevant? To me, taking going through all this information regarding the electron configuration. So the picture that you see here, this is an actual picture for a snowflake, and I think that's pretty incredible. And without studying electrons, electron configuration, behavior of electron, properties of electrons, a picture like this will not be possible using electron microscopic techniques. Okay, so that's in terms of taking a picture of a snowflake. Now, a snowflake, who really cares using these kind of techniques? But when it comes to taking a picture of a ribosome, for example, trying to design a drug or antibiotics to target certain diseases, either cancer treatment, or any other medical conditions. Uh, electron microscopic techniques has added a tremendous amount of potentials in that regard. And without really studying the electron properties, a picture for the ribosome, as you see here, will not be possible. Um, and again, that's all because of electrons and the potentials of electron properties. And beside that, regardless even of electron microscopic techniques and properties of electrons, what you're trying to do, again, you're trying to enhance and improve your problem solving skills and to try to challenge yourself. So please think of it this way, even though it might sound a little bit irrelevant to what you're going to do in the future, but overall, I think it really improves your skills on it gives you better abilities to be a good problem solver in general. But um, electron properties has tremendously helped the scientific community taking detailed picture of a human cell biology, and so on and so forth. Okay, I hope you find this interesting. And as always, please, if you have a question, make sure to reach out to me.